So let's follow these 3 rules to solve the equation. Step 1, you write all the coefficient on the left hand and put a vertical line to separate the right hand, which are 16, 38, and 6. So your goal, ideally, is to write the left hand as 1, 1, 1, 0 everywhere, and then whatever left here on the right hand will be the solution of the 3 variables. This is the same idea as we used to find the inverse matrix. The difference of the inverse matrix is we have 3 columns instead of 1, because we really need to find 9 parameters. But in practice, when I show you this example, I don't need to quite find such an identical matrix on the left. Instead, all I need is to find a matrix like this with 3 zeros under the major diagonal. Such a matrix doesn't matter what is here on the up corner. We call this as up triangular matrix. Now, once you get the upper triangular matrix, I can find the x, y, z one by one by reverse substitution. Let's do it. So step 1, I write this into a standard form, and then you look, the goal is to make this element B1, and then the step 1 is divide 2 to the first row. That's the rule number 1. Then the second step, I'm going to make 2 zeros down here in the first column. I'm going to turn this into 0, turn this into 0. So we apply the third rule. We multiply the first rule by -4, add to the second row, then you get a 0 here. We replace the third row by the -2 times of the first row and add the third row. Then you get a 0 here. So if you follow this operation, let's just do 1. To open 0 in this second row and the first column, I make a -4 times of the first row, add to the second row. So 1 times -4 is -4 plus 4 is 0. That's your purpose. 3 times -4 is -12. -12 plus 15 is 3. And 4 times -4 is -16 plus 19 is 3. Okay, so you get a nice 2 zeros. And then we continue. Your next goal as a step 3 is to make this element 0. 1, I mean, turn this into 1. Then you divide by 3 to the second row. So second row become 1, 1, 2. After this, we only need to make this equal 0. This -6 equals 0. Then I need to add 6 times of the second row to the third row. Now 0 is 0. The first, this is nothing changed. And -1 times -6 plus 0, -1 times 6 plus 6, you make 0 here. That's good enough. And then negative 6 plus 5 in this element, I get this equal 1. 2 times negative 6 is negative 12. And add to 10. Oh no, 2 times 12. And then you get a 2. So in this case, you get the solution. Now, what you can see from this representation, the third row is really matter. That just to tell you, let's translate it back into equation 0 times x plus 0 times y plus 0 times, no, 1 times z equal 2. Then you get the z equal 2. Once you get the z equal 2, now I call it x3. And then you substitute back into the second equation, which tell you this one is x2 plus x3 equal 2. And then that means 2 plus x2 equals 0. Then you get the x2 equals 0. Once you get x2 equals 0, you can plug back into the first equation. The first equation here means the x1 plus 3x2 plus 4x3 equal 8. So what that means, you put this equal x1 plus 0 plus 8 equal 8, then x1 also equal 0. You get the same solution, 0, 0, 2. So you use MATLAB or you use the Gauss-Jordan algorithm, they really work in the same way and it's very efficient. The advantage of this manipulation is doesn't matter you call it x, y, z, or you call it x2, y2, z2. If you write any computer program, you know it's hard to remember all those names. What matters for the solution is the matrix on the left and the vector on the right. All you need is manipulate this. Computers are very good for that. So we look at this example. It could not be solved by the old way, but we can still solve by the Gauss-Jordan algorithm. Well, let's see. We try to follow the Gauss-Jordan algorithm. What are we going to find? So the coefficient matrix, you just select 2, 1, negative 1, 2, 1, negative 1, 1, 2, 1, 1, 2, 1, negative 1, 2, no, negative 1, 1, 2. See, that's the left hand. The right hand equals 3, 0, 0, the same. So if you try to figure out the determinant, maybe it's a good practice, you're going to find that's 0. No wonder, you see, the MATLAB complaint did not give you the solution. Say the matrix is singular. Okay, now let's do it. Follow the same idea. I want to make the first element 1. Then you can divide by 2 to the first row, but that's not a good idea. You get a lot of fractions, nobody like that. You can apply the first row. Swap the first 2 rows, and then you get this one. And then you get the nice one. The step 2, you want to make 2 zeros here. You want to turn the 2 element, the 2 and the negative 1 to 0. All you need is add the row 1 to the third row. This add to here, you get a 0. You can add negative 2 times of the first row to the second row, you make a 0 here. And let's do a one little check. See, the first 1 plus negative 1 is 0 for the first one. 2 plus 1 is 3. 1 plus 2 is 3. 3 plus 0 is 3. That's right. 2 minus 2 is 0. 1 minus 2 times 2 is negative 3. And the negative 1 minus 2 times 1 equals negative 3. We got it. So what's next? You can divide this and this both by, divide the third row by 3, divide by the second row by negative 3. We got this all nice row. But now you started to look, you say, oh, the second row and the third row are exactly the same. What does that mean? That means they're the same equation. You really only get 2 equations, not 3. And the 1 somehow is redundant. Well, what's next? The next, I'm going to multiply negative 1 of the second row, add to the third row. Automatically, the third row are all zeros. You turned all to 0 because you cancel out. So you cannot get any equation from 0 equals 0. In the end, you got 2 equations. The first equation, you read the second line, means y plus z equal 1. And the first equation means x plus y, 2y plus z equals 3. So what are we going to do? You got 3 variables, 2 equations. You got a free variable. You can select whatever number you want. Then let's let this z equal t. If z equal t from the second equation, you find the y equal 1 minus t. And then you plug in z equal t, y equals 1 minus t. Then you add, you have the x plus 2 minus 2t plus t equals 3. Then the x really equal 1 plus t. It's right here. So once you get this, all have the parameter t, you write it back. Oh, I call it x1, x2, x3. Doesn't matter. It equals, that's x, that's y, that's z. I want to separate the constant with the parameter t. Then I might write this 1, 1, 0 in a column, factor out the t. You see 1t, negative t, positive t, factor out the t, I have 1, negative 1, 1. And this gives the solution a geometric meaning. And in geometry, if you learn the Cal 3, you know this is a vector past the point 1, negative 1, 0 past this point. And it's parallel to the vector 1, 1, negative 1, negative 1, and 1. Pass parallel to this vector. So you really get a straight line like this. Pass the point here, and the parallel, the vector v equals 1, negative 1, 1. So you got the infinite many solution, but all the points stay in a straight line.